Hello, ma'am. Good morning to one and all. This is Kenishit. I'm from ECB section. My name is and my roll number is 219518044. And introduction to my topic is non-violent ramps in MEAS. They have been even envisioned as a new tier of memory in server systems, offering comparable performances to DRAM with the durability property of storage devices. Seeing the great value of a large body of prior studies investigated how to exploit NVRAM to benefit future computer systems, yet only recently has the first server-grade NVRAM DIMM product come to market, namely Intel Optane DC Pre- Persistent Memory aka Optane DIMM. The latest characterization studies exposed sustainable descrip- descriptant performance characteristics compared to what we thought before a real products were released. For instance, figure I compares results of the widely used persistent memory emulation platform PMEP and our obtained DIMM server measurement on single-thread read and write bandwidth and latency per coach line axis with a pointer chasing micro benchmark. The micro benchmark randomly accesses a contiguous data region with fixed 64B. By seeing the flowchart, we can see the PMT 6DIMM obtain 6DIMM, and the second flowchart we may know the latency per CL obtained 1DMM and PMEP 1DMM objects by varying the data region size from 64B to 256 MB. We observe a clear inconsistency between the emulation and real system results discussed in detail in the section 1-2B. The other previous NVRAM emulators and simulators also generated uh, different performance characteristics compared to real machine results as discussed in section 2 and section 3. As such, previous NVRAM emulation and simulation tools are insufficient to model modern real NVRAM systems. Moreover, Intel's announcement mentions that the obtained DVIMM adapts on an DIMM buffer structure all through without further details. The obtained curve in figure 1b also shows buffer effects at the sizes of 16 KB and 16 MB respectively. Both indicate the obtained DIMM adopts a much more complex microarchitecture design than conventional DRAM DIMMs. However, most of the existing obtained DMMS studies focused on system-level performances, profiling, and system software design without detailed investigation on microstructure. To achieve our goal, we make the following technical contributions. First step is profiling and reverse engineering framework. And that means we designed low-level profile for non-violate memory system lens, which consists of a set of profiling tools and micro benchmarks to analyze to analyze the architectural and performance characteristics of NVRAM-based memory systems. Lens is designed as the Linux kernel mode. It exposed detailed architectural characteristics of memory systems such as on DIMM, buffer size, on hierarchy, queuing scheme, and the access gradiently on each component. And the second point is real system characterization. We employ lens to perform a comprehensive architecture and performs analysis of obtained DIMM based servers using lens. Our profiling reveals a detailed picture of the obtained DIMM micro architecture. And the third point is NVRAM simulator. We developed a validated we developed a validated cycle accurate NVRAM simulator VANS which models NVRAM based memory system architecture designs based on our characterization. We validate VANs against expensive obtained DMS based real machine profiling. Vans adapts a flexible modulator design which allows users to explore design such spaces with few various architecture designs and extend to simulator to model other NVRAM microarchitecture design. And the fourth point is case studies. We employ Vans to evaluate two architecture optimizations on Optane DIMM, lazy cache, and pre-translation which address Optane DIMM based memory system performances influences in cloud workloads identified by Lens. Then the background and motivation. Overview of our motivation. Recent top 10 DIMM profiling shows different performances characteristics compared to many previous NVRAM studies. However, most of the obtained DIMM studies focused on system performances analysis and system software design. Industrial documents indicated that the memory controller and obtained DMS adapt more complex minor architecture design that conventional DRAM DIMM based memory systems, but without many of the details. These challenges motivate us to explore microarchitecture design and memory system modeling based on real environment products. System Service Organization illustrates an example of obtained AMS based server systems. Obtained AMS denoted as NVRAM sit on the memory bus along the DRAM DIMMs. These are controlled by processors, integrated memory controllers (IMCs). Intel Cascade Lake is the first microarchitecture to support Optane DIMM specifically. Our server systems adopt one or two processor dies in each CPU socket. Each processor die has two IMCs and each IMC supports three memory channels. Each channel is configurable to have 0 or 1 Optane DIM operation modes. Optane DIM operates in one of two modes, memory mode and or app direct mode. This memory mode does not support data precedence. Each memory channel incorporates an Optane DIMM and at DRAM DIMM, the DRAM serves as a data cache of the obtained DIMM. In app direct mode, the obtained DIMMs are used as persistent memory, which unifies the fast access interface of memory. By seeing this image is obtained based on the system configuration. No architecture components. Industrial documents disclose several architectural design components related to obtained DIMM, but most of the descriptions do not provide the details as identified by our study. To ensure data precedence, each IMC maintains a write pending queue WPQ and a read pending queue RPQ to for obtained DIMMs. The WPQ belong to the asynchronous DRAM refresh ADR domain. CPU ensures that the data resets the ADR domain in persisted during power outage. Optane DIMMs supports CPU cache line granularity access. The current implementation adapts 3D X-point clip chips as NVRAM media with a 256-byte access granularity. In addition, each Optane DIMM maintains the buffer inside the DIMM controller. Sub 256-byte write access will trigger a read modify write RMW procedure is in the buffer. Lens low-level NVRAM profile. To address the challenge of the insufficient profiling tools, we purpose of low-level profile offers non-violate memory system. Lens consists of a set of NVRAM profiling tools and low-level micro benchmarks. With detailed performance profiling, Lens also allows us to reverse engineer in microarchitectural design of NVRAM systems and with and DIMM buffers and various control schemes. In this paper, we use Lens to profile the detailed architecture design of obtained DIMM discussed in the section B to be a Lens framework. Lens adapted three key components: probers, to examine the following three aspects of the NVRAM architectural design respectively. Buffer prober, analysis of DIMMS buffers architecture and their properties including buffers A or Q, hierarchy, capacity and access granularity, policy prober, analysis NVRAM controller policies on data migration and multi-DIMM interleaving. Performance prober facilitates the above two probrosto analyze performance characteristics including memory bandwidth width, and the access latency of various buffers and queues in NVRAM, DIMMs, and IMCs. Micro benchmarks Lens provides three micro benchmarks: pointers chasing, overwrite, and straight. Each prober employs customized micro benchmark to trigger specific hardware behaviors. Each leads to different latency and bandwidth patterns with different memory architecture properties. By analyzing the performance patterns, we identify the corresponding microarchitecture properties of parameters. Able to lens overview, buffer and policy and performance problems. And the conclusion is we define Lens and Vance, a low-level performance profiler for NVRAM system and an architectural level memory simulator that models the recently released Optane DIMM memory system using Lens. We perform a detailed characterization of Optane DIMM microarchitecture design. Lens allows users to characterize the performance and reverse engineer the architecture design of real NVRAM DIMM systems. WANS allows researchers who do not have access to obtain DIMM physical devices to explore and evaluate new design ideas on architecture and system. Furthermore, both Lens and Vans are flexible to use with other NVRAM systems beyond the current obtained DIMM design. Thank you for giving this wonderful opportunity.